Hello everyone. We already have the idea of continuity and differentiability from our previous classes, okay? So here we are going to again review continuity and differentiability. So what is continuity? If a function is continuous, then left-hand limit and right-hand limit and functional value at x equals a, all this will be same. Then we can say that the function is continuous. A function will be differentiable if left-hand derivative and right-hand derivative both are same, then we can say that the function is differentiable. So let me write the notations for left-hand limit, right-hand limit, and left-hand derivative and right-hand derivative. So for continuity, if we have to check whether a function is continuous or not, then you know that left-hand limit equals limit x tends to a minus f of x. Right-hand limit equals limit x tends to a plus f of x. This plus and minus are just the directions. So for differentiability, we also have left-hand derivative and right-hand derivative. For left-hand derivative, we have a limit, that is limit h tends to 0, function of a minus ace minus function of a divided by minus ace. Similarly, for right-hand derivative, the formula is limit ace tends to 0, function of a plus ace minus function of a divided by plus ace. So you have to remember these two conditions, left-hand derivative and right-hand derivative. So whenever we are going to check whether a function is continuous at x equals a or not, then we are placing here x tends to a minus, x tends to a plus. But if we have to check whether the same function f of x is differentiable at x equals a or not, then you have to remember that there is a is always. So for differentiability, a tends to 0 always. It may be x equals 1, but we will not input here a tends to 1. Okay, it will be always 0. So if I take any example, you have to check both continuity and differentiability for the same function. So here we have f of x equals x squared and square root of x less than equals 1, x greater than 1. So whenever we have learned limiting concept, then I have mentioned to you that we have to find L, R, and E functions. We have a function x squared, which is defined for x less than equals 1, and square root of x, which is for x greater than 1. So you can see that x less than 1, then we will have x squared. Similarly, for x equals 1, we have the same function, x squared. And now we have x greater than 1, that is for square root of x. So we are going to check whether the function is continuous or not. Continuity at x equals 1. This is given in the question. So we know that for continuity, the condition is left-hand limit must have to be equal to the right-hand limit, and also it is equal to f of a. So if we compare x equals a with x equals 1, then you can easily understand that value of a is 1. That means we have here 1. So at first, let's find left-hand limit. Limit x tends to 1 minus. Similarly, we have the right-hand limit. Limit x tends to 1 plus, because we are checking continuity at x equals 1. That's why I have written here 1 minus 1 plus and f of x. Here we have f of x. We have to understand which function will be placed here out of these 3 functions, and similarly which function will be placed here. So we have already identified that whenever we will find left-hand limit, then the function will be x squared. Whenever we will find the right-hand limit, then the function will be square root of x. We can now easily solve this. That is, here we have left-hand limit, here we have right-hand limit. So once we have identified which functions are leftward and which function is rightward, then we don't need to use minus and plus signs. So we can skip that. Now we can input the value of x. So x squared. In the place of x, we are plugging 1. 1 squared. So 1. So 1 is a finite value. That means limit exists. So left-hand limit exists. Let's see what will be the right-hand limit. Here we have limit x tends to 1 square root of x. Now we can input 1 where we have x. So this is also 1. This is a finite value. That means right-hand limit also exists. So you can see that left-hand limit and right-hand limit both are same. So we can say that limit exists. Now, for continuity, we have also another condition. What is f of 1? We have to find out. So if f of 1 has also the same value as we have for left-hand limit and right-hand limit, then we can say that the given function is continuous at x equals 1. So whenever we will find f of 1, then always check e part. So we have identified that for e, we have x squared. That means here f of x will be x squared. So in this function, we will input x equals 1. So this is very important to identify which one is L, which is R, and which one is E. So it is easy to find now. That is, if we input 1, so we have 1. So that means f of 1 is also 1. So we can see that left-hand limit equals right-hand limit equals functional value at x equals 1. So all these 3 conditions are satisfied. That means we can leave a comment. The given function f of x is continuous at x equals 1. So half part of the total problem is done. Now we have to check whether the same function is differentiable or not. So for that, I am taking the same function in another place. Now we are going to check the differentiability. So differentiability at x equals 1. This is our target. So for differentiability, we have to check total two condition, that is left-hand derivative and right-hand derivative. So if left-hand derivative and right-hand derivative both are same, then we can say that the given function is differentiable at x equals 1. So for left-hand derivative, I have mentioned a formula, limit a tends to 0, function of a minus a minus function of a divided by minus a. Similarly, for right-hand derivative, we have a limit a tends to 0, function of a plus a minus function of a divided by plus a. Remember, for left-hand derivative, we have minus here and here. For right-hand derivative, we have plus here and in the denominator also. So we have to now find left-hand derivative and right-hand derivative. But at first, figure out what is the value of a. So you know that if we compare x equals 1 with x equals a, so value of a is 1. That means, let me write the same thing again so that you can easily understand where we have to input the value of a. You can see here we have a minus a. That means 1 minus a, function of 1 minus a, minus function of 1 divided by minus a. Similarly, for right-hand derivative, limit a tends to 0, function of 1 plus a minus function of 1 divided by plus a. Now, for left-hand derivative, remember the first part is L part and the second part is E part. For right-hand derivative, the first part will be rightward part and the second part will be the E part. So already we have found what is f of 1. Whenever we have checked continuity, we have found that f of 1 is 1. So let me write 1 where we have f of 1. We know this value. Limit a tends to 0 for right-hand derivative minus 1. Now we can give here a big question mark. What will be f of 1 minus a and f of 1 plus a? You can see that when we have to find f of 1 minus a, then we will use left side function. So x squared. That means in left side we have x squared function. In this function we have to input 1 minus a. So where we have x, let's plug 1 minus a. X squared 1 minus a squared. And we can also simplify if we want. So we have 1 negative 2a's plus a's squared. So in this part, let's plug 1 minus 2a's plus a's squared. So this is how we can find the value of f of a minus a's. Now let's find out f of 1 plus a's. At the same time, we are working for left-hand derivative and right-hand derivative. So for right-hand derivative, we have to use this function. So f of x for right side, we have square root of x. So where we have x, we have to input 1 plus a's. Done. We can see that we have left-hand derivative and we have right-hand derivative here. So we can calculate these limiting portions. So let me mention this is equation 1 and this is equation 2. We have 1 and negative 1. To find the limit of any function, we know that we can apply algebraic manipulation technique or chains of variable or L'Hopital's rule or squeeze theorem. So anything can be done. So here we have a's squared negative 2a's divided by a's. So you can now check by plugging the value of a's. So if we input the value of a's here, 0 minus 2 times 0. So in upper part, we are getting 0. In lower part or denominator, we have 0. That means whenever we have 0 divided by 0, we can apply L'Hopital rule. Or we can also use algebraic manipulation technique. So here, no specific method is mentioned, so we can use any one. Let me show this one by 2 methods. First one is algebraic manipulation method, and then by using L'Hopital's rule. So you can apply any one. So we are using here algebraic manipulation. Limit a's tends to 0. We can take a's as the factor. So we have a's times a's minus 2. A's times a's minus 2 divided by minus a's. Now we can simplify again. So here we have limit a's tends to 0. There is a minus coming from the denominator. So we have minus times a's minus 2. So we can now input the value of a's. So a's is 0. We can plug here. It will be negative 0 minus 2. That means left-hand derivative becomes 2. Same problem can be solved by L'Hopital's rule. Since we have 0 over 0, so we can apply L'Hopital rule. L'Hopital rule says that if we have 0 over 0 or infinity over infinity, then we have to differentiate both numerator and denominator with respect to the variable that we can see in limit. So here we have a's as the variable. We have to differentiate both numerator and denominator with respect to a's. So if we differentiate a's squared, it will be 2a's. Differentiation of 2a's is 2. In denominator, we also have to differentiate. Differentiation of a's with respect to a's is 1. Now we have limit a's tends to 0. A minus is coming from the denominator. So if we simplify, we can now input the value of a's. So we are getting 2 times a's, 2 times 0, 0, minus 2. So 2. So it doesn't matter which method you are going to apply. You are going to have the same result. So we have found left-hand derivative. Now we are going to find right-hand derivative, which is the equation 2. We have here a square root minus 1. That means to solve this limit, we have to multiply the opposite similar quantity both in numerator and denominator. If we multiply this, then you can see that same thing are being cancelled. So we have the previous limit. So actually multiplying this opposite similar quantity in numerator and denominator doesn't have any effect. So we have just multiplied this quantity so that we can simplify the given limit. So here you can see that in denominator we have a times square root of 1 plus a plus 1. Now a minus b, a plus b, it will be a squared minus b squared. So right hand derivative equals a limit a tends to 0. Now the simplification will be 1 plus a only minus 1 divided by a square root of 1 plus a plus 1. Now 1 and negative 1 are cancelled. So we have limit a tends to 0, a divided by a times square root of 1 plus a plus 1. Now again, we can cancel the similar terms. So we have 1 in numerator. Limit a tends to 0, 1 over square root of 1 plus a plus 1. So we can now input the value of a. This is the simplified result of the given limit. So we can input a as 0. So it is 1 plus 0 plus 1. We are getting 1 over 1 plus 1. That means 1 over 2. So right hand derivative is 1 by 2. It is also finite. That means right hand derivative limit also exists. But we have to check whether left hand derivative and right hand derivative are same or not. So left hand derivative and right hand derivative. We have found that left hand derivative equals 2, but right hand derivative is 1 by 2. So these two are not same. So we can leave a comment. The given function, that is the main function from where we have started. So this main function is not differentiable at x equals 1. So finally, we can give another comment. The summary is the given function f of x is continuous at x equals 1, but not differentiable at x equals 1. So this is how we can check continuity and differentiability. Now we will solve another problem from modulus functions. So let me take at first a simple problem. F of x equals modulus of x, or absolute value of x. And then we will solve another problem where the function will have, let's say, 2 absolute value quantities. So at first, let's have a look on this problem. We are going to check the continuity and differentiability at x equals 0. Say. So we are going to check the continuity and differentiability for this function. Now, let us focus on the difference between the previous problem and the new problem. Have a look. Whenever we have checked the continuity and differentiability of the previous problem, you have seen that this function is given in piecewise form. We have L, we have E, we have R. So remember that absolute value functions can be simplified to piecewise functions. So if we have absolute value functions, then our first target should be to have the piecewise function. That means we have to convert this absolute value function to piecewise function. Then only we can have L, E, and R. We are going to check continuity and differentiability of modulus of x at x equals 0. So if we go with this technique, then it will be a wrong concept. So don't use this technique. At first, you have to know the correct process. Whenever we will have an absolute value function, your first target should be to convert that function to a piecewise function. So how we can convert? Let's try to learn. We have f of x equals modulus of x. So we know that modulus of 5 will give you 5. Modulus of minus 5 will give you 5. That means absolute value of 5 is 5. Absolute value of negative 5 is 5. That means the inside quantity can be either positive, can be negative. The inside quantity can also be 0. Modulus of 0 is also 0. So we have actually 3 conditions. This inside quantity can be positive, just like this one. This inside quantity can also be negative. Same quantity can be 0, because if x is 0, so we have 0. So we can make 3 functions from this given function. One is plus x, another one is 0, the last one is minus x. So we have found 3 parts. Now we have to also define what will be the domains. So we are now constructing our own function. So you can understand that if the inside quantity is positive, then the meaning is it is x greater than 0. We can think by this way. Instead of x, we will always compare with x minus a. So if we compare modulus of x with modulus of x minus a, where a is any real number, so actually invisibly we have 0 here. That means f of x equals absolute value of x is nothing but modulus of x minus 0. So based on this 0, I have written here, check the continuity and differentiability at x equals 0. For plus x, the defined domain will be x greater than 0. For 0, we will use x equals 0. And for minus x, x is less than 0. So we have constructed f of x. That means the absolute value function is now converted to piecewise defined function. So steps to convert an absolute value function to a piecewise function. So step 1. You may have a general function, let's say modulus of x minus a. It may be also x plus a. Let us work with x minus a. So step 1, you have to think about the inner quantity. Take this out, x minus a, and solve for 0. You will get a value. So step 1 is to find a value of x, where we have to check continuity and differentiability. Step 2. This function f of x equals modulus of x minus a. This inside quantity can be either positive, can be either negative, can be either 0. So for 0, we have already solved in step 1. Okay, in step 2, you have to check this. Then step 3. Step 3 is to make a piecewise function. So f of x, we are using a curly bracket. Now, let's say we have 3 semicolons. Okay. This is x equals a. Always write x equals a because this is coming from step 1. Now, in the first part, you can write x less than a. And in the last part, you can write x greater than a. For x less than a, we will plug the minus part. So minus x minus a. For greater than, we will use plus x minus a. Here, the function is 0. So finally, we have 3 parts: minus x minus a, 0, plus x minus a. So this is how we can construct a piecewise function from a modulus function. So now have a look here. If we write in an arranged form at first work with x less than 0, then x equals 0, and x greater than 0. For x less than 0, we will have minus x. Here we have 0, and here we have plus x. Why I have written in this way? Because at first we are targeting for left, then equal, then right. So we are going to check the continuity at x equals 0. For continuity, you know that we have to check left hand limit, right hand limit, and functional value at 0. It is given. Okay, because we are checking the continuity at x equals 0. So if we compare with x equals a, value of a is 0. Now, let's find left hand limit. So left hand limit x tends to 0 minus f of x. Right hand limit x tends to 0 plus f of x. So let us figure out which function is L. L is minus x. Which function is E, that is 0. Which function is R, that is plus x. That means we have just x. So we are finding left hand limit. That means here we'll have minus x. For right hand limit, we will have plus x. Now let's find limit x tends to 0. No need to write minus above. Limit x tends to 0. So if we input 0, minus 0, that means 0. Finite value, left hand limit exists. Let's input 0 in the right side. So here we have 0. This is also finite. So left hand limit and right hand limit both are finite value and same. That means we can say that since left hand limit equals right hand limit, therefore limit exists, total limit exists. Now we have to check the last condition. What is f of 0? So f of 0 will come from E part. Here is our E part. That means here f of x will be 0. So for E part, f of x is 0. So now we have to find what is f of 0. In the place of x, we are plugging 0. So since it is a constant function, f of x equals 0. If we input 100, it will be 0. If we input minus 100, it will be 0. So anything, if we input, the result will be 0. This is the property of constant function. So we can see that left hand limit equals right hand limit equals functional value. That means f of x, that means the main function is continuous at x equals 0. Done. Let's check the differentiability for the same function. So differentiability at x equals 0. Again, we have ls minus x, es 0, rs plus x. So left hand derivative equals limit ace tends to 0. You know that function of a minus ace minus function of a divided by minus ace. Right hand derivative equals limit ace tends to 0, function of a plus ace minus function of a divided by plus ace. Now we have to input what is the value of a. So A means 0. X equals A, x equals 0. So A is 0. Limit h tends to 0, function of 0 minus h, function of 0 divided by minus h. Similarly, limit h tends to 0, function of 0 plus h minus function of 0 divided by 0. No need to write 0 minus h. Let me write in a simplified form. F of 0 minus h means f of minus h. Then f of 0 divided by minus h. Right hand derivative, limit h tends to 0, function of 0 plus h means function of h only, minus f of 0 divided by h. Now you can remember that I have mentioned to you the first part is L, the second part is E. The first part will be R for right hand derivative, the second part will be E. And we have already found what is the value of f of 0. Whenever we have checked continuity, we have found that f of 0 is 0. So limit h tends to 0, function of minus h, I am giving here a question mark, minus f of 0, that means 0, minus h. Right hand derivative, limit h tends to 0. We don't know what is f of h, but we know what is f of 0, that is 0. Now we have to find f of minus h from leftward function. We have leftward function minus x. That means f of x equals minus x. So from here, we have to find f of minus x. So where we have x, we are plugging minus x. Minus minus plus x. So f of minus x will be plus x, because we have collected the left function. Left function is minus x. Then we are plugging minus x because it is given here. So minus times minus x, that is plus x. Similarly, for this part, we have to check the right side function plus x. From here, we have to find what is f of x. Where we have x, just plug x. Plus x means x only. So we have x here. So these are the side notes. Now limit h tends to 0, h divided by minus h. Limit h tends to 0, h divided by plus h. So we have h and h cancelled, that is 1. And here we have a minus sign, we have minus 1. So left hand derivative is minus 1. In right hand derivative, we have 1. Right hand derivative is plus 1. Both left hand derivative and right hand derivative are finite, but left hand derivative and right hand derivative are not same. So the given function f of x equals modulus of x is not differentiable at x equals 0. So the overall summary is f of x is continuous at x equals 0, but not differentiable at x equals 0. So this is how we can check continuity and differentiability for absolute value function. Let me take another example. F of x equals modulus of x minus 1 plus modulus of x plus 2. So step by step, we have to form piecewise function. Step 1. If we have a general function, let's say x minus a plus x minus b modulus, here we have also modulus. So the previous problem that we have done, here we have only a single part. There is no summation or subtraction terms here. So if we have single absolute value function, then the process is this: step 1, step 2, and step 3. If we have two parts and both parts involves absolute value, then the process is somehow different. So let me write this one. At first, we have to solve this inner quantity for 0. Also this quantity for 0. So here we have x equals a, here we have x equals b. Now step 2, we have to draw number line, and we have to understand out of x equals a and x equals b, out of these two numbers, which number is smaller? Suppose b is smaller than a. We know that in number line we have 0, and these quantities are negative and these quantities are positive. So in number line we have to identify which number is smaller and which number is larger. So in number line we have to locate these numbers in ascending order from smaller to larger. Step 3, we have, let's say, b and a. B is smaller than a. B has come from x minus b. A has come from x minus a. Previously, the function that we have to rearrange or reorder this function because b comes first. B is smaller, so this part should be written at first. So we have to rearrange by this way. Step 4, we have this idea from step 3. Now I am writing in a different way. Here we have x minus b, here we have x minus a. Our target is to identify the domain. At first, always we will consider a number that is on the left side of b. So what will be the mathematical notation for this? It will be x less than b. This number is smaller than b. So obviously x minus b will be minus, x minus a will be minus. For now, please try to write down. We will try to understand this concept whenever we will solve this function. So for now, please try to understand. At first, we will have minus and minus. Then we will take another point in between b and a. This position can be defined as b less than x less than a. Since it is crossing b, so there will be also an equal sign where we have b. So we have identified another domain. It is b less than equals x less than a. For now, please try to write. I will make you understand later. So we can see that we are crossing b. So whenever we have x minus b, the sign will be plus. But still, we are in the left side of x minus a. So for x minus a, we will use minus. Now, finally, we are here. The position will be x greater than a, we're also crossing a. That means it will be equal. So x equals a or greater than a. So it will be plus and plus. So at first, if you are maintaining the order from smaller to larger, then always it will be minus minus, then plus minus, then plus plus. Now we can think about this problem. So we are having trouble to convert this function to a piecewise function. So have a look on step 1 from the general concept. We will take out the inside quantities and we have to find the x values. So step 1, that means x minus 1 equals 0, x plus 2 equals 0. We have to find the values of x. So we have found two values. Which value is smaller? Obviously minus 2. So step 2, plot the number line. This is minus 2, this is 1. Minus 2 is coming from x plus 2. 1 is coming from x minus 1. So we have to think like this way. Now, based on this order, we have to interchange the position of this function. So the function should be in this order. Step 3. Minus 2, 1. Here we have x plus 2. Here we have x minus 1. We will now make a table. At first, x plus 2, then x minus 1, and here the domain. So always I have told you that think about the left side of this number. The position will be x less than minus 2. So x less than minus 2. Now x less than minus 2 means it may be minus 3, it may be minus 100. So we can take any value that is less than minus 2. So let us choose any value, minus 4. So if we input minus 4 here, so total result will be minus 2. So what is the sign of this result? Minus. So that's why minus is coming. Same number can be plugged here. Minus 4, we have minus 1. So the result is minus 5. So the sign of the result is minus. Done. Minus minus. Now let us come here. Its position will be minus 2 less than or equal to x less than 1. So minus 2 less than or equal to x less than 1. So in this point, x can be any value that is larger than minus 2 or less than 1. It can be also equal to minus 2. So we can think about any value in between minus 2 and 1. We can think about 0. So let's say x equals 0. So if we input x as 0, 0 plus 2, the result is 2. That means plus 2. Sign of the result is plus. Now, if we input same value, 0, here, 0 minus 1, result is minus. So that's why plus minus. We can also think about x equals minus 2 because I have given here an equal sign. So if we input minus 2 plus 2 equals 0. So before 0, we can easily think about plus. Okay. If it is minus 2 minus 1 minus 3, still it is minus. Now we have to think about here. It is x greater than equal to 1. So x greater than equal to 1. That means x can be 1 or x can be any value larger than 1. Let's say x equals 5. So if we input 5 plus 2, 7. So it is plus 7. 5 minus 1, 4. That means plus 4. So that's why we have written here plus and plus. Now we can think about the piecewise part. So first domain, second domain, third domain. What is our first domain? It is x less than minus 2. X less than minus 2. What is our second domain? It is minus 2 less than or equal x less than 1. What is our third domain? X greater than equals 1. For x less than minus 2, both x plus 2 and x minus 1 will be minus x plus 2 minus x minus 1. We are removing the absolute value signs, but if we have to remove, we have to give here a sign. Is it plus or minus? So this table is guiding us that it will be minus and minus. For the second domain, x plus 2 will be plus, but x minus 1 will be minus. So here plus x plus 2 minus x minus 1. For the third domain, both x plus 2 and x minus 1 are plus. So this is how we are rearranging the functions. So f of x. Now we can do the simple calculations. Minus x minus 2 minus x plus 1. So it is for x less than minus 2. Here we have x, again plus 2 minus x plus 1. So the second domain is minus 2 less than or equal x less than 1. For the third domain, plus, so x plus 2 plus x minus 1. Now we can again simplify f of x. So if we calculate minus 2x minus 2 plus 1 minus 1. So then x less than minus 2. For the second part, x and x cancelled. We have 2 plus 1, 3. Minus 2 less than equals x less than 1. For the third part, we have 2x, 2 minus 1 plus 1. So x greater than equals 1. That means we have reached to the conclusion. We are able to convert this given modulus function a piecewise function. So this is how we can convert. So now the question is, check the continuity and differentiability, let's say at x equals 1. You can also check the continuity and differentiability at x equals minus 2. So now you know the process how to do. So that's all for today. Thank you.